Bayes formula. Bayes formula is named after Thomas Bayes, Reverend Thomas Bayes, and the work that he did was involve conditional probabilities, and it allows us to look at conditional probabilities in a special way to arrive at what's called posterior probabilities that are ultimately of interest in making a decision. If you haven't read these bullets with these definitions, you'll want to do so, so pause the video and read through those. Before I get into those and before I get to the formula itself, I would like to set some stuff up or motivate us with this example. And so this is from Ott and Longnecker. It's actually problem 429 in the 6th edition there. So banks have to make decisions about loaning out money, and they make them based on the kind of risk or the type of risk a particular person is, and so we're going to look at this kind of situation. And if you think about what a bank might want to know, is they want to know that if somebody is a poor risk loan, maybe we should use the word a high risk loan, but the language here is a poor risk loan. What is a probability that that loan will be defaulted? Okay, so the bankers are interested in this before they start handing out money. Also, they would like to know what's the probability that a good risk loan will be defaulted, or what's the probability that a poor risk loan will not be defaulted. Okay, so these are some things that they would be interested in here. So let's take a moment and try to parse out the important information here. I'm going to let A1 represent the loan repayment situation of a default, and A2 represent a non-default. I'm going to let B1 be the poor risk, B2 a fair, B3 a good risk. Okay, and within the context of this problem, I'm given certain information about these events. In particular, if we look here up front, 1% of loans are defaulted. Okay, so that would tell me in terms of probabilities that the probability of A1 is 0.01. Okay, and then so equivalently, the probability of A2, because A2 is the complement of A1, that would be 0.99 by the complement rule. All right, we also get a little bit more information here, and this first piece of information, or this next piece of information, 30% of defaulted loans went to poor risk. Okay, and this is something the bank could look back at past data and get that kind of information, that you know, of all the defaulted loans they had, how many of those were classified as a poor risk. Okay, so this is actually a conditional probability that we're given. We're given given the loan was defaulted, so that would be A1. We're told that 30% of those went to poor risk, so that would be P of B1 given A1. And that probability is 0.30, 30%. 40% of defaulted loans went to fair risk, so we would have here the probability of B2 given A1. Given a defaulted loan, what's the chance it was a fair risk? That would be 40%. Probability of B3, let's see here, of B3 given A1 is 30%. Okay, and in the last sentence, we're given some information in regards to the non-defaulted loan. And you notice here, I could fill in some of this information into the table. I actually don't really like the way this table is set up because some parts of the table would represent conditional probabilities and some other parts would not. Anyway, so I don't want to get into that here. I'm going to just write out the information on the side. So we have here from the last sentence probabilities, conditional probabilities involving conditioning on non-defaulted loans. So of the non-defaulted loans, 10% went to poor risk. So that's telling us that the probability of B1 given A2 was 10%. The probability next statement here, 40% of non-defaulted went to fair risk. So the probability of B2 given A2 is 40%. And then lastly, the probability of B3 good risk given non-defaulted was 50%. Okay, so we're given that sort of information. With that in mind, and kind of the notation there set up, I want to, in this example, I want to calculate the probability, so it's a probability here, that a poor risk loan will be defaulted. Okay, so what am I given? I'm given that the loan is a poor risk loan. That is, I have that extra knowledge that, hey, this particular applicant is a poor risk. So given event B1, that's why I have that after the given bar, given event B1, what is the probability of A1, or the probability of default? And that's the kind of probability that a banker would want, right? So we want to handle probability of A1 given B1. Now notice we do have the probability of B1 given A1, but we want to switch these two. Now it probably doesn't work out to where I can just do something magical to this number and I get the switched conditional probability. So it's a little more details involved than that. But Bayes' theorem or Bayes' formula allows me to get to this switched conditional probability. And so if we go back up here and look at Bayes' formula, it tells us, okay, so it has these different designations, prior probabilities, posterior probabilities. Ultimately, I want a posterior probability of A1 given B1. And Bayes' theorem says you can get the posterior probability. Would look something like this. Now my A's and B's are, oh, I thought they were switched, but they aren't. Okay, they're fine. So the A's are what's called states of nature. So in the context of the bank example, the state of nature is the type of risk the person is. Okay, so I'm sorry, not the type of risk. That's the observable event. Back up. That's the observable event. We can observe from a credit score that this person is a fair risk, is a good risk, is a poor risk, that sort of thing. The states of nature would be what's going to happen throughout the course of the loan. Is the loan going to be defaulted or not defaulted? Okay, so we want to know something on the probability of some state of nature given some observable event. And Bayes' theorem is really nice for that. It allows us to compute ultimately these posterior probabilities given prior probabilities and likelihoods. Okay, now likelihoods is information or probabilities observed. It looks at probabilities of observable events given states of nature, and those are often probabilities that can be gotten or at least estimated from past data. And so that's what the bank has given us in terms of this information in the last two sentences. These are all likelihoods. These conditional probabilities here, this set and this set, are all likelihoods. Okay, and these probabilities here, P of A1 and P of A2, those are prior probabilities. we want the posterior probability of A1 given B1. Okay, so Bayes' theorem, Bayes' rule allows me to get to that. It says the probability of AI given BJ is, the numerator here is I switch the conditional probability, so it's the probability of BJ given AI times the probability of AI. This is a likelihood here. That's a likelihood there, and that's a prior probability. So the likelihood and prior probability that correspond to the switched conditions for the posterior that you are interested in is what goes in the numerator. In the denominator, what we do is we do a similar computation, except we cycle through every state of nature. And so you see here it's probability of BJ given A1 times P of A1, and plus the probability of BJ given A2 plus P of A2. And so then all the way through P of BJ given AK times P of AK. That's if there's K states of nature there. So the J, that subscript is not changing. The subscript on the A is changing. We're cycling through in this sort of conditional probability times a prior probability through all the states of nature there. Okay, so with that formula in mind, let's go back to the problem here. So Bayes' formula, if I was to apply it, I would have the probability of B1 given A1 times the probability of A1. Okay, then divided by the same thing, P of B1 given A1 times P of A1. Now I have to cycle through this conditional probability and this prior probability again, but go through to the next state of nature. Well, there's only one other state of nature here, and that's the non-default situation. So I'm going to have P of B2 given A2 times P of A2. Okay? So we've got these probabilities, right? We listed them out earlier. P of B1 given A1 is 0.30 times P of A1, which is 0.01, divided by, again, same computation, 0.30 times 0.01. Then plus P of B2 given A2. We got that there above. P of B2 given A2. I'm sorry, this is P of B1. I apologize for that. P of B1 given A2. Okay. That observable event stays the same. The state of nature is what's changing. P of B1 given A2 is 10%. Here it is, 10% there. Times P of A2, that prior probability was 0.99. So that's a 10% there. And if you work through the computation, you'll get 0.0294. So there's almost a 3% chance that a poor risk loan will be defaulted. Okay, that's from this, based on this kind of data. All right, so you can imagine a bank would be really interested in this. Next question, show that the posterior probability of a default given fair risk equals the prior probability of default. All right, so what are we looking at here? We're looking at a particular posterior probability, the posterior probability of default. In other words, P of A1 given a fair risk, that is P of A1 given B2. Let's see what that is. So through Bayes' theorem, that is P of B2 given A1 times P of A1 divided by P of B2 given A1 times P of A1. So similar, or the exact same quantity to start off my denominator there. I've got to cycle through the other to the other state of nature. So it's P of B2 given A2 times P of A2. Okay. So just filling in from the information that we have above, P of B2 given A1 we saw was 0.40. P of A1 was 0.01. So I have 0.40 times 0.01 plus these probabilities were, that was 0.40 times 0.99. And if you work through that, you'll see that you get 0.01, which is what? Which is the prior probability of default. So what is that saying? Well, it's saying that if somebody has a fair risk, that has no bearing on the chance of that person defaulting on the loan. So A1 and B2 are independent events. Okay. Now let's see, why is that the case? Well, if you look back at the problem, if you look at P of B2 given A2 and P of B2 given A1, they're both 0.40, and that's what's driving this posterior to be the same as that prior probability. Okay, this was a short video on Bayes' theorem. I hope that it's helpful.